So in video 2 we're going to look at an application of Newton's law of heating and cooling. So Newton's law of heating and cooling has a model that we visited in an earlier video, but to review it, Newton's law of heating and cooling says that the temperature of an object that's either being heated or cooled is given by T sub r plus the difference T naught minus T sub r times e to the kt. And looks like there's some delete error there. T sub r in this model just represented ambient temperature, or in other words, the temperature of the medium in which you place an object that is then going to either be heated or cooled by that medium. So if you're placing a cold pop out of the refrigerator and setting it down in your room, the ambient temperature of the room will be warmer than the pop and begin to heat the pop. So T naught, or T sub 0, is just the initial temperature of the object that is getting heated or cooled. And K is a constant that you have to solve for. It is dependent on the properties, the physical properties of the object that is being heated or cooled, and T is just representative of time in this model. So we have ambient temperature plus initial temperature of the object being heated or cooled minus ambient temperature times e to the kt, where k is just a heating or cooling constant dependent on the physical properties of the object that's being heated or cooled. So in this problem we have a pot of coffee being brought to a boil. And because it's being brought to boil, we're going to have to make some assumptions. We'll assume that we're at sea level and that it's boiling at about 212 degrees Fahrenheit. Again, it would depend on elevation. It would depend a little bit on how the chemicals in coffee change the boiling temperature of water. But we're going to assume sea level and 212 degrees Fahrenheit as a simplifying assumption. The coffee is then poured into a cup and placed on a table in a room that is kept at a constant temperature of 68 degrees Fahrenheit. So this room is going to start to cool the coffee down. So this is our T sub r, our ambient temperature. After 1 hour, the coffee has cooled to a temperature of 140 degrees Fahrenheit. So the coffee's cooling, so that makes the room our ambient temperature. So just cataloging information, we see T sub r is going to be 68 degrees. T naught, we're assuming it's 212. That might not be the best assumption, but it will work for our purposes. And we're given an initial ordered pair. We're told that at time equal 1 hour, we're not given, we're given an initial temperature, at time equals 0, we have a 212 degree temperature, but we're also told that an hour later the coffee had cooled to 140 degrees Fahrenheit. So we're actually being given a couple data points for the model. So first step in these problems is to set up the model, and K is going to be something that we need to solve for using information about how the substance we have is heating or cooling. So in this case we're going to get temperature as a function of time needs to equal the temperature of the room that is cooling the cup of coffee. So the room temperature is 68 degrees Fahrenheit plus T naught, the initial temperature of the coffee, which we're going to assume is 212, minus the temperature of the room that's cooling the coffee, so 68, times e to the k, we don't know k, we'll need to solve for it, times t. And then we need to simplify this a little bit. This is going to be 68 plus 212 minus 68. That's going to be what? 144? Add back real quick and check. And that's going to be e to the kt. And then what we do next is we need to figure out k. So we grab this data point on the model. This 1 hour caused a decay to 140 degrees, and we plug that information into the model, right? The model is input time, output temperature. So I replace temperature in the model with 140. And we replace time in the model with the 1 hour. And now we're going to need to solve for k, which means we need to get k out of the exponent position, which means we need to isolate base e so we can attack it with its inverse, the natural log function. So first step in isolating base e is to get is to take the 68 that we see right here and subtract it from both sides, which will leave 144 e to the k on the right hand side. 140 minus 68 is going to be, what is that going to be? That's going to be 72. Add back to double check your work. And then we will need to divide both sides by 144 by 144. 144 divided by 144 is 1. 1 times e to the k is just e to the k. And this looks like it simplifies to a half. If we multiply 72 times 2, we get 144. So this looks like it simplifies to 1/2. And now to get k out of the exponent position, I have isolated the base e, so I take the natural log of both sides. So get the natural log of 1/2 equals k, because the k will pop out, and I get ln of 1/2 equals k. And now I'm going to go back to my model right here, and I'm going to update it with the correct value of k. So I'm going to say temperature as a function of time is equal to 68 plus 144 e to the natural log of 1/2 times time. And then I can actually answer question A. So first I have to find the model. Once I have the model, now I can answer questions. Find the temperature of the coffee after 30 minutes. And here we need to be careful. When we created the model, we used this ordered pair right here. The ordered pair that we plugged in to the model to find k was 1 hour and 140 degrees Fahrenheit. So now the model expects time to be input in hours because we used an hour unit in the construction of the constant. So I need to recognize that this 30 minutes is really 1/2 hour. I don't want to plug 30 into the model. I need to plug in a 1/2 hour. And this will equal 68 plus 144 times e to the natural log of 1/2 times the 1/2 hour. And at that point, to approximate the temperature after a 1/2 hour, we're just going to go to the calculator. So let's keep that and slide this out of the way, and we'll input that information into the calculator. So we go 68 plus 144. The e is above the natural log button because they're inverse functions. So e to the, and now I need to put the whole exponent in parentheses. So inside there we're going to put the natural log of 1 divided by 2 of 1/2 times 1 divided by 2, so times 1/2, and then close off our exponent and hit enter, and we have about 170 degrees Fahrenheit. So our temperature is about 170 degrees Fahrenheit. Should be colder than 212 and should be warmer than 140 degrees that it was after 1 hour. Should be a number in between 140 and 212, and it is, so that looks pretty good. Now we can answer part B, determine when the coffee will have cooled to 122 degrees Fahrenheit. So now we're being asked when this happens. So this is a temperature. So we need to go back to our model and replace temperature with 122. And our model is 68 plus 144 e to the natural log of 1/2 times time. Now I need to subtract this 68 from both sides because we have to isolate e to dig time out of the exponent position. So that's going to be what? 30, 52, 54. Subtracting 68 from both sides, add back to check your work. And this is going to leave 144 e to the natural log of 1/2 times time. And then we'll divide both sides by the 144. Divide both sides by the 144. We could also just have found the inverse function for the model and plugged it directly into the inverse function. And that's going to be a 1. Not going to worry about simplifying the fraction because this mess is going to be going into a calculator anyway, so we'll leave it 54 over 144 equals e to the natural log of 1/2 times time. And now I'm going to take the natural log of both sides, the natural log of both sides, which is going to leave me with the natural log of 54 over 144 on the left hand side. This natural log will cancel this e, which will kick down the exponent, which is the natural log of 1/2 times time, and then we divide both sides by the natural log of 1/2 to get the t by itself. Divide by the natural log of 1/2. So our time is going to be approximated by this ratio here, so we'll go ahead and get that with the calculator. I'm going to keep those changes, go to the calculator, and we're going to do the natural log of 54 divided by 144. That natural log divided by the natural log of 1/2, so 1 divided by 2, and we hit enter, and it looks like 1.4 hours. So we got have to wait about 1.4 hours for it to get to that temperature. Does that number make sense? Well, after 1 hour we were at 140 degrees, so about another half hour later we've cooled down to 122. That answer seems sensible, so we will live with it.